So, for example, if Rhodes University set up a groundwater supply scheme, fed that into the municipal supply scheme, how would that work in terms of our municipal bill? Because Rhodes would be supplying water to the municipality, etc. Then it's also around liability. So at the moment, if there are issues with water quality, municipality is liable. If Rhodes University takes on a treatment system, whether it's for their groundwater or for their grey water or for rainwater, they become liable. So at this point, we're trying to keep the systems completely separate, and then but also provide the university with different options, and then they can make a decision based on that information. Okay, some challenges. We actually have no idea really how much water is being used on Rhodes University campus. One of our biggest next step tasks is to go and map out the key meters and see which are working, which are not working, identifying some kind of strategically placed meters so we can start getting a better idea of how much water Rhodes University is actually using. There's water wastage from leaks and overconsumption. Currently the university is being charged an average by the municipality, which just goes up a little bit every year. But it's quite possible that's an underestimate. Then water quality issues. I've mentioned poor monitoring. There are contamination sources. Roman Tandlich has done quite a bit of E. coli monitoring and picked up E. coli at different parts of campus at different times. So that is an issue. And generally the groundwater has naturally high levels of iron and magnesium. So it would definitely have to be treated. Many of the new buildings on campus, particularly the residences, now have dual plumbing installed. But even with dual plumbing, you would have to still treat the groundwater, in particular with the iron and manganese, because it stains and blocks up plumbing equipment. Then there is the issue that Rhodes is the main revenue provider to the municipality, so we can't just cut ourselves off completely from the municipality. The university does want to continue supporting the municipality, but as I said, that is university senior management area to look at and decide on. There's also public access to Rhodes University water, so the public do use bathrooms and collect water on campus when there's no water supply in town, and that's something that the university wants to continue supporting, but of course it is quite difficult to monitor. Okay, so before I move on to the next slide, we're just going to go into a little bit to show you the sort of work we've been doing around the different areas: rainwater, grey water, groundwater. So we'll go into a little bit of detail there and how we've estimated demand. And so I'm going to hand over to Rebecca now. Yeah, thanks.
Thanks, Jane. Okay, so one of the first things we try to do is estimate university water demand, because we're not currently monitoring university water use, which is quite difficult. And our starting point has been to try and estimate what is the use for residents, students and staff on campus, and then day students and staff, because that is relatively easy. You can use a simple water use calculator. It's very difficult to measure water use in kitchens, in laboratories and other uses on campus. So we've used that as a starting point and came up with a rough estimate of daily use for resident students of about 170 litres per person per day. Day staff and students we've estimated at about 30 litres per person per day. And from those figures, we were able, using student numbers, staff numbers, able to come up with daily consumption, monthly consumption, and annual consumption estimates. So annual consumption just for this group of persons on campus and these water users, over 200,000 kilolitres per year. So those numbers we're using at the moment just to make a relative comparison as to how much the various supply sources could actually supplement this particular demand on campus. So it's allowed us to just see, groundwater versus rainwater versus grey water use and municipal supply. If we put those all together, could we try to at least tackle this demand? Okay, so I'm going to start off with rainwater harvesting. And we try to just look at what is the potential for this on campus. We have a lot of roof area, we have a lot of downpipes. We could potentially be harvesting a lot of rainwater. We used a simple water balance model, so don't worry about the detail too much, but just to explain that this water balance model, which Prof. Dennis Hughes helped us with, is quite useful in that it does estimate how much you can harvest throughout the year, and it gives you the frequency of tank storage volume and how that changes. So what percentage of the time is are your tanks full versus half full versus empty? And then it gives you the frequency of supply volume. So you can set the model to a particular daily supply volume. So for example, if you want to supply 1,000 liters per day from your tank, what percentage of time would you be able to supply that volume using your daily to annual rainfall in Grahamstown? So we try to just use an example of a roof area of 500 square meters. Say we have approximately 80 students within that particular residential building. How much could we potentially harvest, and what percentage of the time through the year would that water be available for the use by the building or the students? Okay, so we did this for the tables showing different tank sizes, so 10,000 litre tank up to 50,000 litres. We set daily demand at quite a low rate. This is really just emergency water use at the moment. So on campus at the moment, students do use rainwater for drinking. They do boil it during emergency periods or for flushing toilets. So obviously you can see it goes up from 440 litres per day to 800 for 50,000 litres. The reserve demand is the level at which the tank would drop, and we would then get students to try and use water more conservatively. And then we're able to look at an estimated mean annual supply from those particular tank volumes. We focus in on 20,000 litres and 50,000 litre harvesting volumes. This is because 20,000 litres is what infrastructure and operations told us would be a feasible number of rain tanks, 10,000 litre tanks at each residential building in terms of just the space available, the infrastructure development, the ability to maintain and manage those rain tanks. And then 50,000 litres because that's an optimum sort of harvesting capacity to reduce your spillage. So for 20,000 litres harvesting, you're going to get a lot of spillage. If you're harvesting 179 kilolitres per annum, you're going to lose 109 of that to spillage. But if you're harvesting 237, you're only losing 51 to spillage. So there's much less spillage loss with 50,000 litres. But just to note that your annual harvesting amount is much lower than the demand that you would have for flushing in a student residence of 80 students. So you are only really able to meet a small fraction of the demand if it's just considering flushing of toilets. Okay, then we've looked at greywater reuse. I think Jay mentioned the pilot greywater system that Professor Tundledge from pharmaceutical chemistry is piloting on campus at Robert Sobukwe residence. He's working with a student, Sipom Zibani. We've been working with him closely. And his pilot system is quite small. We've tried to make a comparison with his system and a commercial system of two different sizes. So the commercial system is Treat, a 10,000 litre per day capacity and a 20,000 litre per day capacity. And that's the kind of treatment capacity of the commercial system. Roman's system is able to treat 1,000 litres per day. But if we were to look at the capacity of the system, he would probably only be able to support around 50 students. If you took in water from showers from those students, you would get supplied with an influent of about 5,000 litres, but you'd only be able to process 1,000 litres, and your demand for flushing from those 50 students would be over 2,000 litres per day. If we looked at the commercial systems, the two different sizes, they can support between 100 and 200 students quite well, because your influent from those students would be, between 10 and 20,000 litres, and they would be able to supply and treat that same volume of water, supplying enough for demand for flushing of toilets. Between 4,500 and 9,000 litres would be the demand for 100 to 200 students. The issue comes down to cost as well, and also maintenance and management. So this small system would need to be maintained and managed by Rhodes University. Infrastructure is currently under a lot of pressure in terms of capacity to be able to do that. So what would it mean to roll the system out across campus and have Rhodes try to manage this kind of system versus these two commercial systems, which can be managed and maintained by a private company, but obviously there's more cost that comes with that. So the installation costs are higher, the weekly management and maintenance costs are higher, but then it reduces that pressure on the Rhodes University system in terms of infrastructure and facilities division.
Okay.
So Jane's going to speak about groundwater.
Yeah, so I'm getting a bit nervous about time. Okay, just to quickly give you an overview. So Rhodes has 15 historical boreholes typically used for historically used for irrigation. There's 3 new boreholes on campus drilled by Gift of the Givers. There's also information from some boreholes drilled during the drought in the early 80s. They're no longer around, but their data are around, and that's really valuable for us. So also at the IWR, we've had a couple of students over the last few years monitoring groundwater levels in town and on campus. So we've built up quite a nice set of data. We've just started, we're setting up a groundwater model for campus so that we can look really in quite a lot of detail in terms of sustainable, what is an amount that is a sustainable supply, and is there a better location? You know, do we need to drill a different well field, or can we use the existing network of boreholes on campus? So very briefly, this is some very rough initial estimates pre our modelling. We've looked at an approximate recharge area based on the surface water recharge area of 2.5 kilometres squared. It's probably a bit bigger than this, because groundwater catchment sizes are not always aligned with surface water catchment sizes, but it's probably not that much bigger than that. Then we've looked at the aquifer beneath the campus, which is a Witteberg aquifer, and typically that is between 3.5 and 7.35% MAP of recharge. So why that's valuable is that your recharge amount, or your annual recharge, you don't want to exceed in terms of use. That's kind of your sustainable limit. As soon as you start over abstracting or extracting the amount that's getting recharged annually, you start moving into a kind of unsustainable space. It's an easy way to kind of say, well, let's not exceed that number. A groundwater study just outside of town identified that the Witteberg aquifer was being recharged at, I think it was 5.7% of your mean annual precipitation. So that's the value we've used. And so looking at a few other parameters like storage of the aquifer depth, as I said, very rough calculations. With a catchment area of 2.5 kilometres, our average rainfall 690 millimetres per year, percentage 5.7% of mean annual precipitation recharge. That's giving you a recharge of 81 megalitres per year. Of course, in drier years between 2016 and 2022, and in 1982, we're getting far less recharge, and so we're not making our target. But the way one would manage groundwater is that you would identify a set amount, and there would be some years which would be unsustainable, and there'd be other wet years which you wouldn't you wouldn't increase your use, you'd keep it standard, and so your wetter years would replenish the aquifers, and your dry years would draw it down. So in a drought situation, you would be unsustainably using your water, but once the rains came and started replenishing your aquifer, you wouldn't increase your use, and so the aquifer would replenish. So it's a stable amount that you'd aim for, and you know, hopefully something fairly conservative. And then in terms of quality, I mentioned high iron and manganese. These were some quality tests we took from some boreholes a few years ago. That's Rhodes there. This is a bit of a misleading map because it's actually based on the surface water catchment. The town does that. So that's Rhodes. You can see it sits on top of this Witteberg quartzite, which gives typically quite good quality water, but it's near the boundary between the shale, and this is not a nice clean boundary like this map suggests. It's a messy boundary, which is why we have our high iron and manganese. And so this would have to be treated.
Okay, I know we're running out of time, so I'll be really quick. So we're at the stage now where we're trying to look at mixed supply using a pilot sort of case study at Robert Sobukwe. And what it's shown us is that you really need to consider building specific context in terms of mixed water supply, which is quite important because you have to look at the building design, the plumbing, whether there's space to put in a commercial sewage treatment system, where do you put the storage tanks, how do you get all the downpipes to feed together into one storage tank, how do you treat the water, and so it's given us some interesting insights. At the bottom picture is showing Roman's small pilot grey water system, just so you know what it looks like. But we do have issues of aging infrastructure as well that needs to be considered, so some of the downpipes are leaking. And just to sum up quickly...
Sorry, just to add to that. So in that particular building, only half the roof area would be able to be harvested in terms of rainwater. There are multiple downpipes. So if you wanted to collect that half of roof, you would, in an overground tank, you'd have to put a whole lot of overground tanks in the building. So we were looking at sinking an underground, because it's a U-shaped building. If the costing an underground tank, so all the down pipes could feed into that tank, and so yeah. Anyway, I just wanted to say there's serious restrictions that you'd have to look at. It's not
easy. So just to summarize quickly, rainwater only meets a fraction of the demand for flushing at residences. So potentially the supply is quite small. Greywater meets demand for flushing, and it's optimal to have larger commercial greywater systems, which are more costly. They're able to treat larger volumes of water that you could maybe centralize from a cluster of buildings, residential buildings. But obviously there's a high cost involved with that. I keep clicking, sorry. Groundwater meets demand for flushing and other uses, so there's quite a bit of water available potentially, but you need centralized treatment storage, and that comes at a high cost as well in terms of infrastructure development and maintenance. If we put all these different supply sources together and develop this mixed supply system, it will ensure long-term water security and sustainability on campus, but we have to look at the feasibility in terms of cost, in terms of management and maintenance, and so our plan is to present all of these scenarios to the university, but then they're going to have to strategically decide which pathways to take, what's most cost effective, but also viable and feasible. Thank you.
Thank you very much.